Pre-calculus students, this is our last video lesson, and it is section 6.2 day 1, and we are finishing up our work with vectors. So section 6.2 is going to teach us about the dot product of vectors. So our objectives are we will be able to apply the dot product to vectors and identify the angle between vectors, and finding work, we're actually scrapping that. We had two pieces in there that basically were covered by 9th grade science class, so we figured let's just show you the new stuff. Vectors can be multiplied in two different ways, both of which are derived from their usefulness for solving problems in vector applications. The cross product, or vector product, or outer product, results in a vector perpendicular to the plane of the two vectors being multiplied, which takes us into a third dimension and outside the scope of this chapter. So we're only going to stay in 2 dimensions, and the dot product does that. So the dot product or scalar product or inner product results in a scalar, usually called the dot product. In other words, the dot product of two vectors is not a vector, but a real number. It is the important information conveyed by that number that makes the dot product so worthwhile. So we need to learn about the dot product, and that way we can talk about different features of vectors. So we already know we may use u equals vector pq as notation for u is the vector represented by vector pq when we draw it. And other notations used include our component form AB and then AI plus BJ, where I and J are the standard vectors that have just a horizontal component and just a vertical component. So now, it says vectors are used extensively in mathematics and science applications, such as determining the net effect of several forces acting on an object and computing the work done by a force acting on an object. So again, we're leaving that work. We did a little bit of force in class yesterday, but we're leaving that work piece, saying you did that in 9th grade science, and let's just get to some new stuff. So, new stuff, the dot product and standard unit vectors. Now I want you to see this, but we have been using the component form, and so usually that's what we're going to stick with. And we see here that if you break it apart into those I and J standard vectors that we have, then things work a little bit differently with the dot product. So if we multiply these in the standard form, what happens is we basically end up ignoring the 1, 0, and 0, 1 component vectors, and you just take u sub 1 times v sub 1, and you add that to u sub 2 times v sub 2, which is exactly the same thing we're going to do when we dot product our component vectors. So we find the dot product by taking the two horizontal components and multiplying those together, the two vertical components and multiplying those together, and then finding their sum, adding them. So much easier with the component form. You don't have all of this extra. Again, the reason for the standard unit vectors is sometimes you need to work with a linear system, and that makes it a little bit easier. So now we've got the definition of a dot product. The dot product or inner product of u with the component form u sub 1, u sub 2, and v, component form v sub 1, v sub 2, is what I just showed you on the last page. Multiply those two x components together, multiply the two y components together, and then find their sum. Add it, and you have the dot product. And then we have some properties of the dot product here that we can look at, and it turns out that the dot product is commutative, so u dot v equals v dot u, and if you need u dot u, so you're basically taking the dot product with itself, then that gives you the magnitude of the vector squared. So it's another way to use magnitude by taking the square root of both sides. We could get the square root of u dot u equals the magnitude of u. And then number 3 says take the 0 vector and do the dot product with that and some other vector u, and you'll get 0. And that's because our 0 vector is component form 0, 0. Then number 4, we see that we can distribute using the dot product, and it doesn't matter, it's an associative property here. If you have the parentheses around the v plus w, or you change them and put them around the u plus v, the dot product will be the same. And finally, for number 5, we see that we can use a scalar, and we can multiply that scalar by either of the two dot products components, either u or v, and it will just be distributed, as you work through it. So what they're getting at here is if we have this dot product, cu times v, the c only needs to be multiplied by one of those components, not both of them. And that's what we do as well when we're working with our real numbers. So if it were 2 times 3 times 4, thinking of it as multiplication, you wouldn't take 2 times 3, 2 times 4, and then find the product. You would only multiply 2 times 3, get an answer, and then multiply it times 4. So it follows a lot of the properties that we're already used to. Now, we need to see a little proof of this. So the first one says let u equal component form u sub 1, u sub 2, and v component form v sub 1, v sub 2. And proof property 1. So let's start this way. U dot v. And when we do that, we would get u sub 1, v sub 1, plus u sub 2, v sub 2. But what I want to do is show that I can turn these around. And right now, I already know I can turn these around, so each individual component. And when I do that, I see that now it would be v sub 1, v sub 2, dot product with u sub 1, u sub 2. And that's going to be vector v dot vector u. So the order, it doesn't matter. We said that up there. Property number 1 is all about the fact that it's commutative. You can move those two around. Just breaking it down so it's obvious to anybody. Now, property 2 says, what if we take u with a dot product with itself? So, dot product of those two. Well, if we did that, we would get u sub 1 squared plus u sub 2 squared. Yeah, my u's here are looking a little bit too much like a's, because I was writing sideways there. And if we have that, we think for a second, okay, what if, and this one has to be a little bit ingenious, because remember, we're going for this. We take the square root of u sub 1 squared plus u sub 2 squared and square the whole thing. What does that do for us? And square root and squaring, of course, are going to be inverses of each other. So what that will give us is the magnitude of the vector squared. So that's what we have with u sub 1 squared plus u sub 2 squared. Magnitude of the vector squared. So those are some little proofs of the properties that we have up here. And what we really want to do is be able to use these. So in example 1, it says finding the dot products. Find each of the dot products here. X component times X component plus Y component times Y component. There's your dot product. It's 23. For B, 1 times negative 4 plus negative 2 times negative 3, which is negative 6. And we get a dot product of negative 10. C. Well, I look at C and I think, you know what? I'd rather have this in component form. I don't want to have this with the i's and the j's and all of that. So it is 2 times vector I, which is 1, 0, minus vector j, which is 0, 1, and we need the dot product with that. Again, I'm going to put it in component form before I do that, of 3 times horizontal component 1, 0, minus 5 times vertical component 0, 1. So I want it in component form, and what this is going to say then, 2 times 1, 0 would be 2, 0, minus 0, 1. So that first component form is 2, negative 1. And then for the second, I would have 3, 0 multiplying by that scalar minus 0, 5. So in component form for our dot product here, that's going to be 3 minus 0 is 3, and 0 minus 5 is negative 5. Now it's so much easier to do the dot product because I have it in component form. 2 times 3 is 6. Negative 1 times negative 5 is 5. 6 plus 5 is 11. So don't let that standard form get in your way. Change it into component form and it'll go nice and easy. Property 2 of the dot product gives us another way to find the length of a vector as illustrated in example 2. So let's go back up here. This is the one I focused a little bit extra on. Property 2, because the magnitude of the vector is the length of the vector. So the square root of u times u will give us the magnitude. And on the next page, we actually get to do that. So let's take a peek at this one. And it says, use the dot product to find the length of the vector u. Well, normally we'd just say, let's go ahead and find the magnitude of u, square root of a squared plus b squared. So 4 squared plus negative 3 squared, 16 plus 9, and that'll come out to 5. But what if we did it with the dot product? What if we wrote it out twice, like so, because we know that's supposed to give us the magnitude squared, so let's find the square root of that for that magnitude. So that will be the dot product inside there of the square root of 16 plus negative 3 times negative 3 is 9, square root of 25, which is 5. There it is. We've got it, and it's the exact same answer. So whether or not we use our formula from, well, 6-1, the first day that we did 6-1, or we use the dot product, we'll still get the exact same answer. So now let's move on to another part of our objective, which was finding an angle between vectors. And this one says, let u and v be two non-zero vectors in standard position as shown. So here they are right here. And it says the angle theta that's between those non-zero vectors u and v. Now, you might look at that and say, well, we didn't talk about vector subtraction. What is that? Well, you're going to notice they did not put these together tail to head, tail to head. And so that's why this one is subtraction. But what we really care about is what's theta? You know, that's the angle that we want to find. So the angle between u and v, vectors u and v, is the angle theta, where theta is between 0 and pi, or between 0 and 180 degrees. The angle between any two non-zero vectors is the corresponding angle between their respective standard position representations. So we want the angle that's between our two vectors, and that's what we want to find out. And we need a new formula for that. So we take a look down here, and by golly, they give us one. Theorem, the angle between two vectors. If theta is the angle between the non-zero vectors u and v, then the cosine of theta will equal u dot v, the dot product, divided by, and this is going to be the product of the magnitude of both of those vectors, u and v. So in the end, this is the way most students memorize it, and that's because we have the setup so that we know all we're going to have to do is take the inverse cosine. So on the top, dot product. On the bottom, product of the magnitudes. So there's three pieces to finding that angle. We need to know what the dot product is, and then we need to know what each of the magnitudes are so that we can take the inverse cosine. Now, down here, they do show us the proof, and I want to go through this just because, you know, we're supposed to see the proofs before we actually use something. But we really are, in the end, going to be using this and not trying to reproduce this proof. So we apply the law of cosines to the triangle determined by uv and v minus u in the picture that we have up there, and use the properties of the dot product. So we start off by saying, all right, law of cosines. We've got a side squared. Just to remind everybody, this would be like a squared equals b squared plus c squared minus 2bc cosine of theta. Been a little while since we saw that one. And so that's why all the variables are where they are. Then we get rid of the squared on the left-hand side by saying, well, we'd have to multiply v minus u times v minus u. And if we did that, we would do exactly what we do with any binomials. We would go ahead and multiply using FOIL. So we'd get a lot of multiplication over there. And we notice that there's some things that we could group together since v times u and u times v is the same. So we'd have vector v, its magnitude squared, minus 2uv plus the magnitude of u squared, u dot u, magnitude squared. And then that could be written as negative 2u dot v. Now, if we have that, because, again, you're taking a look at this and seeing what we're going to do is subtract these from both sides. Those are going to drop out nicely, and we get negative 2u dot v equals negative 2 magnitude of u, magnitude of v, cosine of theta. We keep going, and we divide both sides by negative 2 magnitude of u, magnitude of v. Do a little bit of simplifying, and again, there it is. Dot product on the top over the product of the two magnitudes, and then we would take our inverse cosine. So that's the proof. We're not going to have you reproduce that proof. What we really need you to do is actually the math behind this and find those angles in between. So example 3 says, finding the angle between the vectors. Use an algebraic method to find the angle between the vectors u and v. Use a calculator to approximate exact answers when appropriate. So we're going to do the same thing we were doing yesterday. We're going to write it down exact, but we're going to use a calculator in the end to figure out what we need. So right away, I start thinking, new formula, cosine of theta, dot product over product of the two magnitudes. So I need to know what the dot product is. 2 times negative 2 is negative 4. 3 times 15, negative 4, I'm sorry, 3 times 5 is 15. So we'll have negative 4 plus 15. And then I've got to figure out my magnitude somewhere. So I'll do magnitude of u up here. Square root of a squared plus b squared, 2 squared plus 3 squared, or u sub 1 squared and u sub 2 squared. So 2 squared is 4 and 3 squared is 9. Square root of 13. And let me see, I'll make some room over here for the magnitude of v. Square root of negative 2 squared is 4 and 5 squared is 25. So that's the square root of 29. And we need the product of those two down here. Let's keep going. So cosine of theta equals 11 over, and then we need the square root of 13 times 29. So you figure out what 13 times 29 is, and that's 377. And now we're set to say we want to find the angle. So if we need to find the angle, we're going to use inverse cosine of 11 over the square root of 377. And that will give us theta. So let's see what we get. Inverse cosine of 11 divided by the square root of 377. And there we are. So to 3 decimal places, 55.491 degrees. That's the angle between the two vectors. So we used an algebraic method to find the angle between the vectors, and at the very end we grabbed our calculator and we punched it in. So let's try B. And B, this would be a good one for you to stop the video, do it on your own, see if you can find it, and then come back and check on it. So cosine of theta equals dot product over the product of the two magnitudes. So let's get going. So dot product, 2 times negative 1 is negative 2, plus 1 times negative 3 is negative 3, and I'm going to go ahead and do the next step for our numerator there. That would be a negative 5. And now I need to stop and figure out what my magnitudes are. Magnitude of u, square root of 2 squared is 4, 1 squared is 1, square root of 5. Magnitude of v, we've got negative 1 squared, which is 1, negative 3 squared, which is 9, and 1 plus 9 is 10, square root of 10. Neither of those two could be simplified, and we probably wouldn't anyway, because we can multiply square roots times square roots now for our product of the magnitudes. So we've got the square root of 5 and the square root of 10, and that'll give us negative 5 over the square root of 50. And you certainly could simplify now by making the square root of 50 the square root of 25 and the square root of 2. So that would give you 5 square roots of 2. 5s would cancel out, negative 1 over the square root of 2. But we are just going to punch it into the calculator, so whether or not you want to do that or not, if they say we have to write down everything exact first, well, then we have to do it. We have to write that down. And you could even rationalize the denominator if you wanted to. But we know we're just going to end up punching this in. So the cosine, inverse cosine, I say that, and then I'm hoping some of you recognize that angle. But let's just go back to using the calculator for inverse cosine of negative 1 over the square root of 2 equals theta. Because if you do rationalize the denominator, you get negative square root of 2 over 2, which hopefully you're saying, oh, that's a 45-degree angle, and go from there. But let's go ahead, because it's in fourth quadrant. Our angle is in third and fourth quadrant. Actually, it's a little bit in first, third, and fourth quadrant. We're going to go ahead and do second inverse cosine of negative 1 divided by second square root of 2. And it is 135 degrees. So like I said, you may get a feel for it as you're going through. You might start remembering square root of 2 over 2, but in the end, put it in the calculator so you see how it all comes together, the angle that is between these two. Now, if vectors u and v happen to be perpendicular, so that is if the angle between them is 90 degrees, well, then when we find the dot product and we have to multiply by the cosine of 90 degrees, well, the magnitudes multiplied by the cosine of 90 degrees is going to give us 0, because the cosine of 90 degrees on the unit circle is 0. So if they're perpendicular, the dot product will come out to be 0, because the cosine of 90 degrees is 0. Now that sounds special. They probably wouldn't have told us about that if it weren't special. And that is called orthogonal vectors. And the vectors u and v are going to be orthogonal if and only if u dot v equals 0. So we've talked about parallel vectors, how parallel vectors, you'd notice one is just a scalar of the other one. It's been multiplied by a constant number for both of the components. But to check for orthogonal vectors, we're going to have to do the dot product. And when we do the dot product, if we get a 0, they're orthogonal. So the terms perpendicular and orthogonal almost mean the same thing. Well, yes and no. Perpendicular, is forming that 90-degree angle. Ortho means to make straight. So yes and no, they almost mean the same thing. The zero vector has no direction angle, so technically speaking, the zero vector is not perpendicular to any vector. However, the zero vector is orthogonal to every vector, because if we take a vector 0, 0 and find the dot product with any other vector, we're going to get 0. So except for the special case, we're going to look at orthogonal and perpendicular as being the same thing with our vectors, so forming that 90-degree angle. Note, two vectors are parallel if one is a scalar multiple of the other. I had mentioned that just a little bit ago because I don't want you to forget that over the weekend. If we take some scalar and multiply it times our component form and get a new vector, well, then they're parallel to each other. They're still in the same direction. So example 4 says, let's prove some vectors are orthogonal. And I remember, all that I have to show is that the dot product is 0. So if we take 2 times negative 6 plus 3 times 4, do we get 0? Negative 12 plus 12 is in fact 0. So the two vectors are orthogonal. Orthogonal. There we go. Oh, my O looks kind of weird there. So dot product of 0. There's our proof right there. It's an algebraic proof, of course, that the two vectors are orthogonal. All right, now, little exploration says. Angles inscribed in semicircles. Figure 6.18 shows angle ABC. So come on over here and look at ABC right there, inscribed in the upper half of a circle. And remember, that's called a semicircle. And x squared plus y squared equals a squared. Now, we need to look at this for a second and realize that means that if we do x squared minus a squared, that would give us negative y squared. Now, how did I get that? I just subtracted a squared from both sides and subtracted y squared from both sides. There's manipulation that can take place here, but we want to remember that it can happen in any form. So remember this, x squared plus y squared equals a squared, but we also should be looking out really for anything where we see the squareds coming back. So number 1 says, let's make a 2. All right, so this will be negative 2, 0, and this will be 2, 0. Find the component form of the vectors u, which is vector BA, and v, vector BC. All right, well, let's do that. So for vector u, which is BA, tail, head, we're going to have to do our tail to head, which means we'd have negative 2 minus x and 0 minus y, which would be a negative y. And then we do the same thing for vector v, and v they said was vector BC. So tail and head, so that's going to be 2 minus x and negative y. Again, head minus tail was the rule that we had for putting these in component form. Now, number 2 says, let's find the dot product and see what happens. Okay, well, let's do that. So the dot product, u dot v, would be negative 2 minus x times 2 minus x, because those are the two horizontal components, plus negative y times negative y. And I'm just on the lookout here because as you go through this, you realize, ooh, I'm going to have some squareds. So x squared plus y squared equals a squared. Well, they told me to put a 2 in for a. I better be watching for that. X squared plus y squared equals 4. All right, so we go ahead and do the math. So first times first, negative 4. Outside times outside plus 2x. Inside times inside minus 2x. Last times last plus x squared. And then we'll add a y squared. Oh, there's x squared plus y squared. Because they told me that we had a 2 for a, x squared plus y squared equals 4. So positive 2x minus 2x is going to be gone, and x squared plus y squared equals 4. Well, look at that. We get a 0. Their dot product was 0. So the vectors are orthogonal. So quite a bit more algebra there than we had done before, which would tell us that that angle theta that's between the two is pi over 2 or 90 degrees. Now, 3 says, let's just do this generically for some a. All right, so I'm going to keep the x squared plus y squared equals a squared. And I'm going to go back to the original drawing, and I'm now going to ignore this negative 2 and 2 business, and I'm going to find the component form and do the same algebra. So this time we would get negative a minus x, comma, negative y by our head minus tail rule for u. Vector v would be a minus x and negative y. Again, head minus tail rule. So u dot v will be a minus x times, negative a minus x times a minus x plus negative y times negative y. We go ahead and do our FOIL. Negative a squared plus ax minus ax, which are going to drop out again, plus x squared plus y squared. Well, ax and negative ax drop out, and we have negative a squared, and then x squared plus y squared is a squared. And again, we see that that's 0. So in a semicircle, what they're trying to get at here is that when we have a semicircle and we form those two vectors so that basically where they meet is on the circle, you're always going to have orthogonal vectors. They will always be perpendicular vectors. And there it is. So that is the last video for this year. Woohoo! And there is 6-2 day 1 assignment. So you'll go ahead and complete that assignment. And then on Monday, we'll have a day of review. Tuesday, we'll take our little quiz on 6-1 and 6-2. And we will be finished for this year.